Good morning. Today we are delighted to welcome Dr. Seema, Associate Professor at SGT University, Gurugram. She is the Chief Investigator of C2S program under the Ministry of Electronics and IT, Government of India, and has also served as a faculty fellow at IIT Delhi. With over 11 years of teaching and research experience, Dr. Seema has published more than 35 research papers, holds 6 international patents, and it is the proud recipient of the Best India Research Award 2022. She is also an active member of IEEE and ISTE. We are truly honored to have her with us today to speak on the theme From Quantum Physics to Quantum Devices, Bridging Theory and Technology. A warm welcome, ma'am.
Thank you so much, ma'am. And first of all, I would like to thank Dr. Parvatham, ma'am, that she gave me this opportunity to express my views that how computing mission is going on and how we could become the part of that mission that has been developed by in the September 2024 by our government of India, because already I'm the part of India Semiconductor Mission, and I hope soon I will be the part of Quantum Mission also. And I hope because most of the candidates I'm watching here, that mostly participants are from the ECE background, and definitely from the ECE background, and from the physics background, they could be the part of quantum materials and devices. That is one of the domain in our quantum mission, and for other mission, for other hubs also, we can say for other domains also, even for quantum communication, for quantum computing, and for quantum sensing also. So other fields could become the part of this mission, and it's an honored ma'am, and thank you so much once again, and thank you to the Sairam institutions. So shall we begin? Could we start?
Yes, ma'am.
Okay. Is it visible?
Yes, ma'am, it's clearly visible.
Okay. Okay. So today I am presenting this session on the topic of quantum physics, how we have moved from the quantum physics to the quantum devices, and we are basically bridging theory and the technology as well. So first of all, if we start with the term quantum, actually the quantum word specifies that how much, right? So how much is the, in the term of quantity we described it. Okay, so quantum is basically, it relates to the energy as well as the matter. Okay, and quantum word basically refers the how much smallest it could be, right? So smallest means it represents the discrete unit of any physical property, that could be energy as well as it could be a matter. If we talk about other light, right? So the quantum part of that light could be a photon, right? And if we talk about the electricity, so a quantum of that electricity, it could be a electron, right? So quantum particles, so there are three types of particles we could see in quantum states, right? So one category is fermions, second category is bosons, and third category is composite particles, right? So fermions, basically these are the particles that are made up from the matter, and in normal routine we are watching it, that is electrons, protons, neutrons, these are the parts of fermions. Next, if we talk about the bosons, right, these are the particles which are force carrying particles, right, and these are the particles which are the protons, gluons, W and Z bosons, right, Higgs bosons and gravitons. And if we talk about the third category, that is composite particles, that is mesons and the baryons. Okay, so quantum, basically the term that comes from the Latin word, that means how much, and it is the smallest as possible, and we could say it is the discrete unit. okay, photon and electron kind of things. So quantum technology, actually the base of quantum technology comes from the principle of quantum mechanics, right? Previously we were doing our work on the classical technology, or we could say the physics behind that. Classical technology was the classical physics, and the physics behind the quantum technology is the quantum physics. Okay, so previously the terms we were using in our classical physics, now our National Physical Laboratory, with the help of metrology, they are inventing, they have proposed new SI units for quantum physics. Okay, so soon it would come in the market, right? So if we talk about the quantum technology, actually quantum means very fast. Okay, that means who are computing the values in the terms of 0 or 1, right, or the combination of both 0 or 1 in a very fast, or we could say ultra fast manner, right? So this is the quality of, we can say this is the most quantitative feature of quantum technology, right? And moreover, this secures the communication, and they also precise our sensing technology. Okay, but I would like to add over here that either we are talking about the quantum computing, or we are talking about the quantum communication, or we are talking about the quantum sensing, right? Just like three domains are in the quantum mission, but for three domains, the base behind of that domains is the quantum materials and devices. So if you know about that quantum materials and devices, then only you could apply the applications in further domains, right? So so everything should be aligned, that what, for which applications we are going for, and what could be the materials and devices could be the best possible ways to solve that applications. Okay, so what are the different key concepts if we talk about? So first thing we all know, the thing is qubit. So qubit is basically a quantum bit, and the shortest form is called qubit. It can be a 0, it can be a 1, or it can be 1 and 0 at the same time, and that condition is called superposition, when it is 0 as well as 1 at the same time. The second thing is entanglement, right? Actually, this is the state sharing condition, okay, in which either those states are very far apart, but they are able to share their state. Okay. Third thing, one by one, I will explain all these concepts, the quantum concepts. Third concept is tunneling. As we all know, the concept of tunneling. Tunneling is basically when the particles pass through a barriers, right? But previously we were talking about the normal classical tunneling, but nowadays we are talking about the quantum tunneling. Okay, so there is a difference in between both the tunneling. Okay, later on I will explain it. Next is the interference. As we know, the interference actually when the when two states are available at a different places, right? And how those quantum bits in those states are communicating to each other, right? So that is called interference. Actually, it helps in the quantum algorithms. Okay. So, if we talk about the quantum revolution, actually the first revolution in quantum was seen in the year of 1900 to 1930. At that time, various theories were given by our eminent scientists, like Planck's theory came, Einstein's theory came, Schrodinger equations came, Heisenberg uncertainty principle came, right? So these were the theoretical revolutions came at the time of 1900 to 1930. These theories were proposed by them. Next, the second revolution that we are watching it from 1935 onwards. So you could see here that nowadays computing, sensing, communication, materials and technology. So previously This was the only theory part, but in second revolution we are talking about the technology. Okay, and IBM is playing the major role when the second revolutions came. So we could see over here in 1935 the EPR paradox was there. Then Bell's laboratories, right? There was an inequality in 1964. In 1970, the quantum information theories birth done. Okay. Then the first conference on physics of computation, and that was co-hosted by IBM and MIT, right? So I already told you that IBM plays a major role for that. Next, the topological quantum orders come in the year of 1982. Then the cryptography technology comes, right? And that also being done by the IBM. Then for the teleportation, that is a part of quantum communication. So that comes in the year of 1993. Then in the 1994, there were a further algorithms was given by the Shor's factoring algorithm for solving this communication part, right? So whatever be the problem, then it got corrected by the quantum error correction in the year of 1995. Okay. Then the criteria further how we could build up a quantum computer, right? So that criteria is called De Vincenzo criteria, right? And that built up by IBM in the year of 1996. Next, the different topological codes came in the year of 1997, and one by one they implemented by the IBM, right? So further experiments being done by the IBM in the year of 2001. Okay. Then the first circuit came, that is quantum electronic devices is demonstrated in the year of 2004. Then a superconducting qubit, that is transmon, came in the year of 2007. Further, if we talk about that, what they did in the coherence time, yes, so the qubit came, superconducting qubit came in the year of 2007. Then the work on coherence time, it could tested by the IBM in the year of 2012, that how this coherence time can be improved. Then using the codes, right, given by the IBM, they demonstrated this thing in the year of 2015. How this improvements has been done with the help of code. Okay, then IBM makes quantum computing available on IBM Cloud. Uh, if later on we have an hands-on experience, right? So at that time I could show you that how with the help of IBM Cloud we could make the quantum computing available. Okay, so that has been done with the IBM in the year of 2016.
ரிசோர்ஸ் பர்சன் நீங்க கொடுத்துருங்க சார் ஸ்டார்ட் பண்ணுங்க மேக்ஸ்னா ஓவரால் மிஸ்டேக் நடத்தப்போது சார் அது ஒன்றுனா ஓவராலாக தான் இருக்கணும் மேத்ஸ்க்கு வேற அவரெல்லாம் வேற யாரும் வேற தான் இருக்கணும் கிராஃப் தியரி எல்லாம் இருக்கலாம்
அதெல்லாம் இருக்கு
டாபிக்ஸ் எக்ஸாம்பிள்ஸ்
போட சொல்ல கிராஃப். ஆமா, கிராஃப்னா ரொம்ப இம்பார்ட்டன்ட். நம்ம அது வேணுமா கரெக்டா அவர் சொல்றது.
Thank you. Okay, so in the year of 2017, that quantum's demonstrations has been done. Next, what is the difference between actually in the classical computing versus quantum computing? So if we talk about the classical computing, that could be done with the help of bits only, and if we talk about the quantum computing, that is being done with the help of qubit. Okay, and if we talk about the operations, how many operations could be performed to do the same calculations? If we see the difference, so in classical computing, if you are having the n qubits, right? So classical computer will do 2 raised to power L operations to perform the same calculations, right? Right? If a one quantum operation on L qubits would done. So classical computer will take 2 raised to power L operations, but quantum operation will do only L qubits operations. Okay. If we talk about the 500 qubits, okay, let's take the example of 500 qubits. So you could see here that a classical computer will do 2 raised to power 500 operations to perform a calculation, but a quantum will do that operation only in 500 qubits. Nowadays, if anyone is talking about that they have created a quantum computer of 500 qubits or 1000 qubits, so at present they have not invented the quantum computer, but yes, they have invented the supercomputing facility, right? Because in quantum, because for supercomputing facilities you are doing 500 operations, but for the spin up and spin down for other operations you are doing and you are using another 2000 bits. Okay, so that is the part of supercomputing, but not is the part of quantum computing. So for quantum computing, that is only possible that if you are having that number of qubits and that the same number of qubit operations you are performing, that is comes under the category of quantum computing, right? So if you see these operations, so on a classical computers like 2 raised to power 500 operations, so you could imagine that how incredible amount of time they are going to be take by a classical computer, right? So for the complex operations, we generally prefer the quantum computing because they are ultra fast computing states. Okay, so number of qubits increases the performance gain over classical computers, and that grows exponentially due to the parallelness of operations. Because in classical computer, 0 and 1 operations they are being performed one by one, or we can say sequentially, but the operations that are performed in quantum computing are the parallel one. So if we see in short, the quantum computing who follows the principles of quantum mechanics to process the information, and yes, who describes, and the quantum mechanics that describes the behavior of very small systems that we call microscopic systems like photons, electrons, atoms, molecules, and many more. Okay. Now come to the principles of quantum mechanics and quantum computing, right? So you could see here that is the quantum computer. Okay, so there are basically 5 principles of quantum computing, right? So first is superposition and qubits. So qubits, if we are talking about, that is the quantum bit. So quantum bit is generally a 0 or 1 or a combination of both. If we are talking about the combination of both, that means that comes under the category of principle of superposition. Okay, so next is the entanglement, third is the quantum interference, fourth one is decoherence, and fifth one is measurement and collapse. Okay, let's start with the qubit. So I told you that a qubit have a 2 states, either 0 or 1. Okay, or maybe the combination of both, that comes under the category of superposition. But if we are only talking about the 0 or 1, that means the 1 state will be the spin up state and 0 state will be the spin down state. When it happens, when this spin up and this spin down happens, when an electron is placed in a magnetic field, okay, then the spin of the electron is, if it is aligned with the field, then it is a spin up state, or if it is opposite the field, then it is called a spin down state. Okay, so nuclei of atoms actually exhibit the same property. Okay, and it can set the spin state of an particle using energy pulse. Okay, further, if we represent 1 and 0 using electron spins, that is called as qubit. Okay, so spin up state represent 1 and spin down states represent 0. Okay, and furthermore, these states could be represented by electron charge instead of spins. Okay, so either 1 or 0. So you could see here, this is the bit, okay, 0 and 1. This is the q bit. Okay, so if we are talking about the classical computing, they only talk about the bit, and if we talk about the qubit. Okay, so that actually talking about the quantum twist. Okay, so you could see over here this psi is equals to alpha 0 plus beta 1. Okay, and this value is 1 and this is the value 0, and actually we define these values on this sphere always. Okay, so this side could be the 1, this side could be the 0, and if it is in the middle one, so the value would be 1 under root 2, 1 under root 2. Okay, so such type of combinations are happened in the qubit. So qubit is the shortest form of quantum bit, and it is the basic unit of the quantum information. Okay, so if we use the units in the in classical info to access to represent the classical information, so we actually use bits per second, bits per this, right? So if we do that computing in with the help of qubit, so we will represent qubit per second, right? So as previously I told you that national physical laboratories are working on that is the form of superpositions. Okay, and yes, you could see here a qubit can exist in a weighted combination of 0 and 1 simultaneously, and if mathematically we represent it, so it is psi is equals to alpha 0 and beta 1. Here alpha and beta both are the complex numbers, but when you add it on with the help of mode, so alpha square plus beta square would become the value 1. So it's a real one. Okay, next we talk about the superposition when the value is 0 and 1 simultaneously. So that is the condition of superposition. Okay, so it is the actually the measurement of superposed qubit, right? Who actually destroys the superposition and will yield either a 0 or a 1. If we do the measurement, so the superposition things will get disturbed. Okay, and further, if the operations can be performed on a superposed qubit without destroying the superposition. So these are the things. Look, yes, the spin state of a qubit can be a superposition in at the simultaneously both 0 and 1 is there, right? But when you go for the measurement, so that superposed qubit destroys. Okay, so at that time it would be either 0 or 1. Okay, now further operations can be performed so that superposed qubit, right? They won't be able to destroy the ability of superposition. Okay, so leave the superposed qubit. So there are the three things. One is the qubit when there is only 0 and 1 state. When we are talking about the superposition, when 0 and 1 are parallel in the same state simultaneously. Third, we are talking about the superposed qubit that is required when we want that during measurement the superposition principle should not be get disturbed. Okay, or should not be get destroyed. Okay, so here we could see here when a photon is passing through a half silver mirror. So here you could see one detector is over here and one detector is over here. Next, we talk about the quantum interference. So you could see here that how these states are communicating to each other. So this is the state is called quantum interference. Okay. So further, you could see here that this is the another way how they are communicating with each other, because qubits are there, right? Nowadays, the testing is going on that are able to communicate with each other or not, right? This is the main thing. If they would be able, if they would become able to connect with each other, to communicate with each other, then only the ultra fast computing could be possible. Okay. So this is the another way of quantum interference. Okay, let's talk about the superposition as I told you, right? So in that state, when this is the state when you are in a state that it may be or may not be. That is the state is actually called superposition if I talk in the layman language, right? But and this state is only possible until it is measured. Okay, if it is measured, then only you would be assured that either it is a 0 or 1, otherwise you are in a position that it may be 0 or may be 1. So that is the state is called superposition, and this position has been established, drawn with the help of quantum, and we are taking a very good example and a very layman example, like we are using a example of cat throat. Okay, so you could see here that if a cat is in a box, right, so we could just think that either the cat is alive or dead until it is observed. Okay, so you could see over here, like this is the experimental setup. Okay, this is the radioactive atom. Okay, this is the detector. Okay, it would detect that either cat is alive or cat is dead. Okay, so this is the experimental setup. So here radioactive atom comes, right? So when it comes, the hammer goes here, right, and it breaks this poison bottle. Okay, when this poison bottle break down, so the cat would become dead. Okay, so this is the possibility, right? If we when we measure these things, or we could say that when we observe these things, then only we would be able to get it that whether the cat is alive or the cat is dead, right? Otherwise it is quite not possible to get. You are in the state of may or may not be, and that is the state of superposition. Okay, so here you could see how it works. If the atom decays, right, so the Geiger counter triggers, right, hammer falls, flask breaks, and cat dies. If the atom does not decay, right, so nothing will happen and cat will be alive, right? But before opening the box, the atom is in a superposition state, right? So you could see here, this is the superposition state, 1 by under root 2. Either it is decayed or it is not decayed, right? So this makes the cat state also superposed, right? So the cat state also superposed. This is the cold state, superposed qubits. What I was saying, that neither 0 nor 1, right? So you could see here, decayed one means alive, not decayed means dead. Okay, and you could see over here that I was talking about it. Uh, yeah, yes, you could see over here that this is the spin up state, listen to one, and this is the spin down state, right? And in between this there where I was talking about, that 1 by under root 2 is here is the position, right? So that is the position where superposed qubits are there. That is, you never know that either it is a 0 or 1. Okay, it may be both 0 and 1 at this state. Okay, so this is the principle of superposition. This is the principle of superposition. Next is the principle of entanglement. Okay, so when we talk about the two particles, right, that can be, yes, you can communicate to each other, right, whether they are very much far apart, right, even in the billions of light years, right, but whatever the operations we are performing at one particle at a one end, so the same operation is possible to perform on the other hand. So that thing, that is called the entangled state, right? So in a descriptive manner we could see here, so two particles can also be prepared in an entangled state, where performing an operation on one particle performs the same operation on another, right? So this is the state of entanglement. Next, you could see here that multiple operations can be performed on particles in this state. without destroying the entanglement or the superposition of either particle. So this is the state of entanglement, because whenever we do observation in the case of superposition, so their superposition principle get destroyed. Okay. Next, if you want to measure the spin of either particle from this one or this one, right? So measuring the spin of either particle destroys the superposition of both states, but places both particles in a distinct state. So superposition state get destroyed, but the places of those particles in a distinct state will remain the same. Okay. Then entangled particles can be a large distance, as I have told. So even it could be the even billions of light years. So you may see over here, right? So this is they are very much far apart, right? Or we could say light years apart, right? So if the two entangled photons are created with the opposite spin, right? So measuring the one spin as a up and will instantly make the other spin down if they are light years apart, right? So this is the state of entanglement where two or more quantum particles can be linked so that the state of one instantly affects the state of other, no matter how far they are, right? So how far apart they are. So this is the principle of entanglement. Here we could see in a very layman form. So until you observe the poles, so what will happen? They are at the far apart. You could see they are at the very far apart. So what happens here? Here the first one is yellow. So you could see here the other below is also yellow. Okay. Here this is the red and this is also red, right? So what happened actually over here? This is the condition of entanglement when you are doing one operation, okay, at a one end, so the same operation is performed on the other end because they are interconnected, right? So the distance doesn't matter, but yes, they are connected. Okay, so the objects remains connected even over vast distances, right? So scientists think of entangled objects as really being a single object. Okay, actually they are entangled to each other, but actually, as from the view of scientists, they are actually a single object. Okay, so this is the principle of entanglement. Next, we talk about the quantum interference. Okay, so you could see here there are two interference. One is the constructive, another one is the destructive. Okay, constructive interference is when the two waves, right, or we could say the quantum states combine, right, combine each other, and this is the state when the quantum states cancel each other. So this is called destructive and this is called constructive. So why there is a requirement of this quantum interference? This is required to amplify correct solutions and thus to suppress the wrong ones, right? To suppress the wrong ones. So this is the resultant wave Z, and here you could say that is the destructive interference, because whatever be the here, its opposite was here, so they got cancelled here. So that's why we are getting only Z. Here you could see this and this. Both are the same amplitude they have, so that's why this amplitude has got added up. Okay, so you could say this is the constructive interference, right? So why quantum interference is required? It is actually required to amplify correct solutions and to suppress the wrong ones. Okay. Next is the principle of decoherence. Okay, so you could see over here again. Taking the example of example of cat. So you could see here, this is actually the quantum physics. Okay, so if in that this is 1, this is 0, okay, and we are making them apart, right? So previously they were coherent, right, and now we are doing decoherent. So here this classical physics gets separated out from this one. Okay, so this was the state of quantum physics, and this is the state of classical physics. So you could see over here how this quantum decoherence is explained by the thought experiment, Schrodinger's cat. cat. Okay, so what actually happening in decoherence? Actually, qubits lose their quantum properties. Okay, quantum properties due to the interaction with the environment. Okay, so the qubits, when it is in the case of superposition, when they are getting measured. Okay, so at that time also superposition get destroyed. Okay, another thing, when qubits with the effect of external environment, if qubit loses their quantum properties, right, and it causes the loss of superposition as well as entanglement. Okay, so that is the state of decoherence. In superconducting qubits, electromagnetic noise, or we could say vibrations, can cause decoherence within microseconds. Okay, and it limits the time available to run quantum algorithms. Okay, so it actually within the seconds, or we could say within the microseconds, the noise or vibrations and electromagnetic noise, right? These are the causes, these are the factors which causes decoherence within microseconds in superconducting qubits, right? So it limits the available, okay, to run the quantum algorithm. So you want to run the quantum algorithm. So these are the things which are getting disturbed, like your superposition, right? Another is the entanglement. Okay, and third one is the in the time of decoherence. Okay, so it happens here due to the external environment. Next, measurement and collapse. Okay, so when you measure a qubit, okay, so at that time what happened? Superposition collapses, or we can say destroyed. Okay, to a definite state. Either it would be 0 or 1. Either it could be 0 or 1, and the original quantum state get destroyed, because at that time, because we are talking about the superposition, and superposition is a state when 0 and 1 both are at the parallel time, right? But when we measure the superposition state, the superposition get destroyed and the superposition collapses to a definite state. That means either 0 or 1. So this is the measurement and collapse, right? So you could see here, this was the quantum state qubit, but after measurement it becomes a classical bit only. Okay, so quantum state has collapsed. So this was the thing, under root 3 by 2, 0 plus 1 by 2, 1. So here you could see the probability of getting 0 is 1 under root 3 by 2, the whole square, is equals to 3 by 4 is the 75%, and probability of getting 0 is 1 by 2 square is equals to 1 by 4 is the 25%. Okay, so that means after measurement, okay, so the probability of getting 0 is 75% and probability of getting 1 is 25% in the case of qubit. Okay, next we talk about the classical versus quantum physics, because these are the basis of the classical computing and the quantum computing. Okay, here you could see, this is the example of classical physics and this is the example of quantum physics. So you could see here in the classical physics nothing is coming over here, and in the quantum physics you could see here, right, and after this it is a very small one. Okay, what actually it's happening, because in the classical physics the things are in the form of deterministic, right? There is a continuous energy level. Here you could see, here is the discrete energy level, right? Here the value is deterministic, but here is the value is in the probability manner, right? So here in classical physics the Newton's law was there. Okay, that means they were shown that if the ball is going up it would get down due to the gravity, but quantum works on the uncertainty principle. Okay, so this is the quantum physics, right? So it is actually no requirement that it should be explained at the atomic and microscopic world. Okay, very minutely. Then only we will be able to understand what is the classical physics and what is the quantum physics. Okay. Now, if we see here the example of swinging pendulum, Okay, so how energy is being quantized? You could see over here, if there is a large amplitude, so that means there would be a large energy. If there is a small energy, so there is a small amplitude. Okay, and in the Planck's constant, what was the value? E is equals to hf, right? So large amplitude means large energy, small amplitude means small energy, right? And moreover, the energy exists in discrete packets, and those packets are called quanta, right? So this is the physics behind the quantum mechanics. Okay, I hope in the communication you have heard the word quantization. Okay, okay. So that this is also comes from that point of view also, because when in the quantization we see the graph is like this one. Okay, so this quantization came from that part. Okay, so whatever be the energy, so depending upon that energy, that amplitude will vary. Okay, okay. So if the energy is high, the amplitude is high. If the energy is low, the amplitude is low. So this is the concept of energy quantization. And yes, that oscillator analogy, yes, told you that if the energy is high, so the quantum, so the step would be high. If the energy is small, so that step would be very small. So this is the oscillator energy has been established in the energy quantization, right? Okay, so here we could see energy quantization, that was I was talking about. Um, yeah, here we could see. Yeah, here you could see in single electron transistors, you could see over here, this is the quantized steps we are watching over here, right? So this is the concept of quantization is being used in single electron transistors. So, and yes, this is the example actually I was looking for. Yes, you could see here that energy energy level. So I told you, if the energy level is high, so the quantization is high. Okay, if the energy level is low, so the quantization is low, right? And depending upon this energy, the density of state is being defined, right? In the quantum well, in the quantum wire, and in the quantum dot. Okay. Okay, so next is the photoelectric effect, very basic one. Okay, so here you could see that when this light ejects electrons. Okay, if the frequency is greater than threshold, right, and the intensity irrelevant of photon energy, right? Okay, intensity irrelevant if photon energy is less than work function. Okay, so the work function matters. Okay, the photon energy is less than work function, so intensity is irrelevant. But if the frequency is greater than threshold, so light ejects electrons, okay, from the metal surface, right? And this is the theory given by the Einsteins, and he also won the Nobel Prize. Okay, here you could see flashlight E is equals to hf, right? Here h is the Planck's constant. Okay, now we talk about the wave particle duality, right? Here we will talk about the de Broglie's wavelength, that is lambda is equals to h upon p, and h is the Planck's constant. Here you could see this is a double slit experiment. Okay, there is a one slit, and here is the double slit experiment that talks about the Young's double slit experiment. Okay, that was given by that. Okay, so you could see here that the wave comes over here, right? Then it got diffracted and the particles came. So this is like the concept of that we have seen in the photoelectric effect. Okay, so you could see over here the light is coming, and through these two slits, right, it is going in the two directions, and they are combining in this format, right? Here you could see here, this is the maximum point. Here you could see this is the another maximum, maximum, and maximum, and the other point in between it is, right, where two waves are combining. So this is the maximum point, and in between this is the called minimum point. Okay, so this is the first screen and this is the second screen. Okay, so in the form of interference and then diffraction. Okay, so this is the wave particle duality. What duality? Duality means dual behavior of what? Of light. Okay, so that means a light have a dual behavior. That means it is have wave like nature and it is also have a particle like nature. Okay, so this is so when we talk about the wave like nature, so that is explained through the interference and diffraction, and we talk about the particle nature, so that is the concept given by photoelectric effect. Okay, so these are the two examples. So that was given by the wave part, that comes under the category of wave particle duality. Next, Heisenberg uncertainty principle. Here you could see here this is the H dash, right? There is a one cross is there. So this cross represents the reduced Planck's constant. Okay, if your value is delta x delta p is equals to this, so the value would be so H dash, or we could say the reduced Planck's constant value is h upon 2 pi. If your actual Planck's constant value is divided by the value of 2 pi, so it becomes the reduced Planck's constant. So you could see over here that the photon is being incidented over here. Okay, now it got scattered at this side, and here it is the recoiling electron. So scattered photon is this side and recoiling electron is this side. So Pi and Pf. Okay, so here is the low energy, okay, and low momentum. Okay, so delta x represents uncertainty in position and delta p represents uncertainty in momentum. Just give me 2 minutes break. Okay, so we were talking about the uncertainty, Heisenberg uncertainty principle. Okay, so here you could see, yes, right. So it is actually defining that how positions are uncertain, right, right, and how this scattered photon, and you could see this recoiling electron. So here is the low positions, right, and low in momentum. Okay, here is the high position and here is the low momentum. Okay, so what actually this principle states, it states that there is a limit to the precision, right, with which certain pairs of physical properties such as position and momentum can be simultaneously known. So this comes under the category of Heisenberg uncertainty principles. And remember this here Planck's constant value is the reduced Planck's constant. That is actually Planck's constant is divided by 2 pi. Divided by 2 pi. Okay, so next is Schrodinger equation. Yes, this was the foundation of quantum mechanics. So previously I have already explained this with the example of that cat, right? Right. So how this behavior is described. So it actually governs the behavior of quantum systems at atomic, or we can say at the nanoscale level. Okay, so psi x, right, this is the wave function, and this is the value of probability density. So what is the probability? Either 0 or 1, right? So an energy quantization arises from boundary conditions. Okay, that condition arises. So here you could see this is the equation. X represents the position, E represents the energy, H represents the Planck's constant, V represents the potential energy, and this is the Schrodinger wave equation, and this is the second derivative with respect to X. Okay. Next, yes, I was telling you about the tunneling, right? As we know, the tunneling is when particles cross the barrier, right? Particles cross the barrier. So you could see here in classical physics, this was the concept of passing the energy barrier, right? This was the concept of passing the energy barrier. But in quantum physics tunneling, right, or we could say quantum mechanical tunneling, this is the thing that these particles are, or we can say electrons, right, can pass through this potential energy barrier. So this is called quantum mechanical tunneling, right? This phenomena we are already using from the last various years, but now in the quantum physics we are incorporating this quantum tunneling behavior. Okay, and this is basically the principle which is being used in the tunneling diodes, STM, and nuclear fusion also, right? So this is the difference between the classical tunneling and the quantum tunneling. Okay, this is the concept. Okay, so where a particle can pass through a potential energy barrier without having enough energy to cross that barrier, so that is called quantum mechanical tunneling. So that is called quantum mechanical tunneling. Next, yes, quantum Hall effect. Okay, so you could see over here. So this is quantum Hall effect, right? So this is the waveforms you could see over here, right? This is the magnetic field. Yes. So see over here, this energy, about energy I was talking about too, right? And this is the quantization level. This is the different quantization level. Yes. So here you could see if the energy is low, the quantization level would be low. If the energy is high, the quantization level will be high. There is nothing, so it's nothing. So here again the energy is high, right? So that's why this quantization level is high. Okay. So this is the quantum Hall effect, right? So it is actually a phenomena that an atom that can be explained at atomic or subatomic level, right? So that can be explained with the help of classical physics, because we are using the classical physics example, less energy and less amplitude, greater energy and the greater amplitude. Okay, so these are the theories that has been used. Is the wave particle duality we have used, superposition we have used, entanglement we have used. Okay, so this is the and if we are talking about the quantized Hall resistance, so that value is h upon and e square. Okay, and 2D electron gas we generally used in magnetic field, and this is the example is being given by. So this position is the half one and this is the one. Okay, so in the case of magnetic field, this is the quantum Hall effect. Okay, next we talk about the Josephson junction. Previously we know about the PN junction. Okay, but what is this Josephson junction, right? So that is the part of only PN junction which we use in the diodes, which we also use in the transistors as well, right? But this is the concept which we use in the superconducting tunneling effects. Okay, so this is the very ultra sensitive magnetometer. So you could see over here, here is the superconductor, here is the superconductor. Okay, because in PN junction, that is one semiconductor, say in between there is a junction, that is PN junction. But here is the one superconductor, here is another superconductor, and in between there is an insulator. Okay, so this a thin insulator is sandwiched between the two superconductors, right? So there is a current flow J across the junction in the absence of an applied voltage. Okay, and this current depends on the tunneling probability of the electron pairs, right? So this type of junction is called Josephson junction. So here you could see, and that is possible with the superconductor. So you could see over here, they have not applied any voltage, but still they are getting the current. So that is the that is called Josephson junction, and that is designed with the help of superconductors, and in between there is an insulator. So you could see here, this is the copper pair, this is the energy level, and you could say with the help of the superconductor, and if this is moving from this end to this end, so you could see, yeah, right? So from this end the electrons are moving to this end, from this end the electrons are moving to this end, right? Because both are what, superconductors, and in between there is a insulator. Okay, so there is a current flow across the junction in the absence of an applied voltage. So this is very ultra sensitive magnetometer. Okay, and the superconducting is used in the tunneling effects. So this is the Josephson junction concept. Okay, next we talk about the quantum materials, right? So when we start with the quantum materials, actually we are talking about very macroscopic properties which are dictated by the quantum mechanics. Okay, and the examples, key examples, we are able to take it to the materials, so we can say spin liquids, topological insulators, and superconductors, right? And this quantum materials, as I have already told, that these are the foundations for quantum computing, for spintronics, and quantum communication, and quantum sensing. So this is the foundation for other domains. Okay, let's talk about the classes of quantum materials. Yes, you could see over here five types of classes. We could see topological insulators, right, that are insulating in bulk. So you could see here insulating in bulk and conducting, and their edges are being conducted. Okay, next we talk about the 2D materials. Okay, so 2D materials are, as we know, graphene, MOST, and hexagonal BN we used. In the case of superconductors, right, in the previous one I told you, in the case of superconductors we are using this copper one. Okay, so the copper pair formation, and that means zero resistance. Okay, then bare direct semi-metal. So you could see here, this is bare semi-metals and this is direct semi-metal. So later on I will explain this. Another one is quantum spin liquids. Okay, another one is quantum spin liquids, that are the exotic entangled states. These are the exotic entangled states. Now first one is the topological insulator. So you could see here, here is the bulk valence band is over here, conduction band is over here, right? And you could see the surface states, one moving up, moving down, right? Another one going opposite to each other. One are coming closer to each other, the two are moving apart from each other, right? So here you could see that insulating in the bulk, right, and metallic states on the surfaces or edges. Okay, examples are BIS2, BI2, SE3, BI2, TE3. Okay, and they follows the time reversal symmetries also, and applications are in the spintronics, low power electronics, and in the quantum computing. Next, 2D materials, graphene, DMTs, and XCNs, LDHs, and others. So here you could see that actually they are having very thin layers. You could see the whole example. They are having very thin layers. Okay, and every material has their own quantum properties. Okay, and which one we were using? Graphene, that has having the high mobility. MOST, they are semiconducting. Hexagonal BN, they are insulating. Okay, next is the tunable band structures. Okay, via strain, doping, or stacking. So, and the examples for these 2D materials are, they are being used in the quantum sensors, photo detectors, and for the flexible electronics. Next is the superconductors. Okay, that coppers, is being used for that purpose. Okay, so we make the proper pair. Okay, and because of superconductors, if two superconductors are connected with with the help of insulator, so it becomes the Josephson junction. Okay, so there are two types of elements actually exist. So type 1 and type 2. Type 1 exists which are elemental, and type 2 which are high temperature couplets, okay, and iron penticides, and their applications are in the MRI machines, quantum circuits, and maglev trains. And you could see, because why, what is happening, because they shows very zero electrical resistance below critical temperature. Okay, so that's why they are called superconductors. So high critical temperature couplets. Okay, so there are two types of semiconductor: type 1, type 2, and zero electrical resistance in between if they are below the critical temperatures. And with the help of copper pair formations, so electron phonon interaction, so that is possible to make the superconductors. Next is the valence and direct semi-metal. So you could see here, this is the direct point, and these are the veil points. So two. So you could say this is the direct point one, and in this Fermi arc there are two veil, means two direct points are available, and these are called veil points, and the arc is called Fermi arc. Okay, so what are these? Actually, they host relatively quasi particles. They are quasi particles, and in between gapless electronic states protected by symmetry, right, and exhibit chiral anomaly and unusual magneto-resistance. If you have studied carbon nanotubes, right, so there are different formations have been done in between the graphene, right. So there is a one category that is chiral anomaly. Okay, so they exhibit chiral anomaly and unusual magneto-resistance in between, and the applications of these materials is in spintronic devices, high mobility transistors, and the topological quantum computing. Okay. Next is the quantum spinning liquids, which are being used with the help of chemistry persons. Okay, so no conventional magnetic ordering even at low temperatures, right? But they are having very strong quantum entanglement among spins. So you could see here they are having very strong entanglement among spins. You could see same spin, and they are having very entanglement. Okay. Next, strong quantum entanglement states. Next is they are having the predicted states: Kitave spin liquid, resonating valence bond states. Okay, and the applications are is being used if we are doing any quantum computation and there is a fault, right? So fault tolerant quantum computations. So for these applications, this quantum spin liquids are used, and for the study of exotic phases of matter, then we could use this quantum spin liquids, right? So basically, they are not having any magnetic ordering, right, even at low temperatures, but yes, they are having very strong quantum entanglement among spins. So this is the basic speciality of quantum spin liquids. Next, quantum
Uh,
dots.
I'm sorry to disturbing you, ma'am. Shall I take 5 minutes break, ma'am?
Five
Shall we
minutes
take?
break. Okay, we will join 11:15.
Yes, ma'am.
Okay, okay.
Ma'am, shall we resume this session?
Yes, ma'am. Shall we start?
Please, ma'am.
Okay. So let's talk about the quantum wells, nodes, and wires. Yes. So we could see here, this is the quantum dot. Yes, this is the quantum dot. Here is the density of states. You see, these are the parallel lines with respect to energy. In quantum wire, so here is the one edge is the shortest one and another edge is the biggest one. So here you could see that with respect to energy, the density of state is like this. Okay. Next, if we talk about the quantum well, right? So you could see here this is the energy, and with respect to this energy, this density of states are moving from at this level, right? So this amplitude actually depends upon the energy level, how much energy we have. So depending on that, this amplitudes will vary. Okay. So we could see here these applications, LEDs, lasers, and single electron transistors. Yes, so with the help of quantum dot, we design the single electron transistors. Okay, LEDs and lasers. Okay, so if we see that what is this quantum dot? This is actually a zero-dimensional confinement, right? And this is atom-like discrete energy levels. Another, if we talk about this quantum wire, this is 1D confinement, right? And here is the conductance quantization is there, right? And third one is the quantum well. This is 2D confinement, and here you could see these bands. These sub-bands are the discrete sub-bands. These are the discrete sub-bands. These are the conductance quantization, and here is the atomic-like discrete energy levels. Okay, so these are the three categories, dot, wires, and quantum wells, which are being used. Next, uh, what is the base of carbon nanotube? Right. So in carbon nanotube, basically we use the graphene, okay, and other 2D materials. So what happens in the with the help of this graphene, and why we use graphene basically, because it is having a high mobility and zero band gap. Okay, and furthermore MOST S2 and similar materials as the semiconductors can also be used for carbon nanotube, but primarily we use the graphene. Okay, so here this is the graphene sheet. Okay, okay, and now with the help of this graphene sheet, you could see here this is the multi-layered graphite. Okay, now we rolled up this and we make this a single wall carbon nanotube. Okay, so this is the rolled one. Now multi-layered, right? So in between there are multiple layers of carbon nanotubes, right? So that means, so there are two types of carbon nanotubes. One is single wall carbon nanotubes. This is the single wall, and this is the multi-wall carbon nanotubes. Okay, and carbon nanotubes actually are the next generation transistors. Okay, and we are able to make these devices with the help of these transistors. Okay, so this is the metallic and the semiconducting based on chirality. So I told you that when we talk about this graphene in detail, right, so there are multiple characteristics, right? So on which this graphene is based. Okay, so one is the chirality. Okay, so this graphene sheet is being rolled and it becomes the 1D structure. So this is the basic specialty of this carbon nanotube. And how this, if we talk about this structure and its working principle, so you could see here, this is a single, so you could see over here, this is again gate, source, drain, substrate. Okay, this is the carbon nanotubes and this is the dielectric layer. Okay, so here you could see in between source, drain, and here this is a single walled carbon nanotube. Okay, so in that case, if single, or we can say the array of carbon nanotubes, right? So they would become the part of channel. Okay, and the gate configuration, that is black, top, or wrap, right? So they will behave as a gate. Okay, so there is a single, otherwise there is a array, or that means either it's a single wall CNT or multi-wall wall CNT. So that is the place where this channel is being established in carbon nanotube field effect transistors. So in that, what is the working principle of this? That what this gate do? This gate voltage modulates this carrier density in carbon nanotubes, right? And the chirality decides its metallic or semiconducting behavior, that it is a metallic behavior or it is a semiconducting behavior. So it is being decided by the gate voltage. Okay, so this is the carbon nanotube, right? And this is the instance CNT regions in between under the gate. Okay, so you could see over there, right? So this is the carbon nanotube field effect transistor structure, and this is the um, IV characteristics. Okay, so this is the drain source voltage, and this is the drain current. Okay, so you could see here, this is the demonstrating the gate controlled current modulation. Okay, so you could see here when this value is 0.3 volt, and when this gate to source voltage is 0.4 volt. So you could see here, this is the waveform, this is the current value, and here you could see how much variation is there in this current value. Okay, so with only minute difference of 0.3 to 0.4 volt, okay, and at a very low voltages you are getting a very high drain current. Okay, so this is the speciality of carbon nanotube field effect transistors, and which are the foundation for further quantum devices. Okay, so you could see how rapidly it is increases. Okay, next, FinFETs and scaling, that has already been, we are using at a various levels. So they are having multiple fins in between. Okay, and short channel effects are being reduced in the 3D design. Okay, because 3D designs, the channel structure has been improved, and that automatically has improved the complete performance of that transistor. Okay. So this is structure of the FinFET, right? This is the insulator, bulk SCI. This is the front gate. This is the back gate. These are the fins. This is the drain. This is the source, right? Gate, and this in between is the gate outside. So there are three fins are being used. Okay, now, but actually it is because I told you that they are reducing the short channel effect. So that means they are improving the noise ratio, that is ion divided by ion, right? And they are also lowering the drain induced barrier lowering, fine. And they have improved the subthreshold slope. So here we could see that how much this subthreshold slope has been improved, right? So in this case we are able to see it as that it has been improved. Okay, so these are the device characteristics of FinFET. Next, we discuss about the resonant tunneling diodes. Yes, about tunneling diodes we all know. Okay, but in resonant tunneling diodes, what is the basically things are going on? So this is the characteristics are exactly same. You could see over here that have been shown in tunneling behavior by the tunneling diodes, right? This IV, this is the peak voltage, this is the this is peak voltage, this is the valley voltage, this is the valley current, and this is the peak current, right? And this is the negative differential resistance in IV curve, right? The curve is exactly same in resonant tunneling diodes as we have seen in the tunnel diodes. Okay, okay. So here we could see the basic construction of RTDs. Here is a resistance thermometer, right? And this is a insulator. This is the insulator. This is a resistance thermometer. So you could see here is the connection to leads. Here is the connection leads. Here is the connection to leads. This is the sheath cover. Okay, and this is the insulator. So this is the basic construction of resonant tunneling diodes. Okay, and what is actually happening over here? Actually, it is a double barrier quantum well. Okay, and electrons tunnels resonantly when energy aligns with confined states. Okay, and this NDR region, negative differential resistance region, actually this is the region when current falls with increasing voltage beyond resonance. Okay, so in that case, current rises to IP at VP and then drops to IV at VB. Okay, delta I and delta V define NDR region. Okay, and these are useful for if we need high speed devices, oscillator and multi-value logic. So this is the resonant tunneling diodes. Okay, and what are the applications for this? These are being used in high frequency oscillators. And because it exploits NDR for stable oscillations at gigahertz and terahertz ranges. Further, for high speed switching circuits also, because it provides ultra fast transition due to sharp NDR behavior. Furthermore, in the terahertz and microwave devices, yes, because they enables compact sources and detectors at very high frequencies. Next one is the multi-value logic systems, yes, because they allow more than two logic states for efficient computing. Next, memory devices, right, because they are being used in bistable circuits for fast and low power storage. Okay, so there are two logic states, 0 and 1, or we can say these are used in the memory devices because they are used in the bistable circuits. Next is the quantum computing applications, because they support tunneling based operations at nanoscale, so that's why they are being used in quantum computing elements also. Next, I was talking about the single electron transistor. So here you could see there are two tunnel junctions. This is the gate. This is the gate voltage. This is gate insulator, source, drain. But here is an island. Okay. Here there are two tunnel junctions which are being used. Okay. If we make this in this format, so this is the capacitor. This is resistor. So capacitor. Here is the electron reservoir, okay, and here is in between is the island, okay. And what is this island? Okay, so this small island coupled by tunnel barriers to source and drain, and gate controls this island potential. Okay, and single electron tunneling, what it does, it produces Coulomb oscillations, right? You could see here it produces Coulomb oscillations. Okay, and what is the working principle? So Coulomb blockade occurs when charging energy E, right, is greater than equals to kT. Okay, that Boltzmann constant and the temperature. Then this Coulomb blockage occurs when charging energy E is greater than kT, right? Because it operates on the principle of Coulomb blockade. Okay, that is single electron control. Okay, and the structure island plus tunnel junction plus gate capacitor. Okay, and it shows Coulomb staircase. You could see this Coulomb staircase in IV characteristics, or we can say this is the oscillation, single Coulomb oscillations we are watching here. And what is this? It is extremely sensitive to gate voltage. Okay, and this is the average number of island electrons. Okay, and here it is the voltage. Okay, and this is the concept of single electron transistor. Now, what are the different applications of single electron transistors? Yes, this is being used in ultra low power electronics, in the charge sensors, in the nano electronics. If you want to build up the devices beyond CMOS, right? So you use the single electron transistors based devices. Okay, then in quantum computing, because it is useful in qubit readout and control due to sensitivity of charge states, because I shows you that because it is extremely sensitive to gate voltage, right? So because of this sensitivity, they are useful in qubit readout and control due to sensitivity to charge states. Metrology, yes, because it's having application in defining current and charge standards at the quantum level, because it is using only a single electron. Okay, so that's why it is called single electron transistor. So that's why it is being used to set up the charge current standards in the case of metrology. Okay. Next, what are the different challenges in quantum technology have been faced? You could see here, this is the classical scattering, and one is the quantum scattering, right? In classical scattering, there is not a concept of coherence and decoherence, but in the case of quantum scattering, this is the concept. Okay. So, for if we talk about the scalability, yes, building large, stable quantum systems. Okay. Next, decoherence and noise. So first is the scalability, because it is able to build up the large and stable quantum systems, right? That is the thing, that are we would be able to make as much scalable as we want. Let's see, this is the challenge. Okay. Next, decoherence and noise. Yes, as we have seen that the constructive and the destructive coherence. Okay. So in that case, we are not sure that qubits are would be should not be easily disturbed, but yes, due to decoherence and noise, qubits are easily disturbed, right? So we need the improvement in coherence uh, codes. Okay. So this is the another challenge. We want that our qubit should not be disturbed. We want this technology to be as scalable as possible. Then error correction. If there is a in somehow there is a error. Okay. So we require another qubits. Okay, that is called physical qubits. Okay, to detect or correct those errors, right? So if for performing an operation we require 500 bits, right? So that means apart from this 500 qubits, we need more bits if we want to correct that error. Okay, so that is the challenge, that how we could communicate with that, right? Next, high cost and infrastructure. Yes, because we have to work in a low temperature, right? So that's why cooling is the concern, right? And the fabrication part is highly expensive in the case of quantum technology. Okay. Next is the talent and standardization gap. Okay. If we see this thing, because quantum is a very new field, and the expertise in that case is very much limited, fine, and the common frameworks is required. Okay. If those frameworks would be enhanced, right, and quite obvious the expertise is required to make the standard at that level. Okay, the training is being needed. Okay, the major talented person is required to overcome all these challenges in quantum technology. Now further, what are the different applications of quantum technology? So if we are talking about at the molecular level, so that means drug discovery and molecular simulation is the major application of the quantum technology. Yes, nowadays we all talk about the AI, right? So if we want to run anything, right, we already have various algorithms on different languages, right? But for the quantum algorithms, we need AI acceleration. Okay. Next, material design and secure communication. Yes, because quantum materials and devices, two things are the major building blocks for the quantum communication, for the quantum sensing, right, and for the quantum computing, right? So these is the major applications of quantum technology. So we need it on a very high basis. Okay. So if we talk about the various quantum uh, techniques, okay, that has been used in our quantum mission, right? So because we are having four hubs in our India, okay, under quantum mission, and 6,000.5 crore has been already been granted to these hubs. And under these hubs, IIT Delhi is associated with quantum material and devices, uh, and IIC Bangalore is associated with quantum computing. IIT Madras is associated with quantum metrology, and quantum sensing as well, with CDOT, and IIT Bombay is associated with quantum communication. Okay, so these are the four hubs has been established under National Quantum Mission by the Government of India, and they are like the hubs. They are the four hubs, and furthermore, apart from these four hubs, they are establishing more spokes, right? And further spikes. Okay, so the model is hub, spoke, and spike model. Okay, so under this category, various proposals are being given, are coming from this end, right? If you want to establish your teaching labs, if you want to start your minor programs. With the help of AICT in quantum, right? So they are giving you the grants for that also, and you may apply for other proposals also, which one have already been. They have floated it, and for the last 6 months, you are able to see that various proposals are coming from the quantum end, and in future also they will call more and more quantum related proposals. Okay, so you must be active on a Department of Science and Technology uh, website. Okay, so regularly check that website, and I'm sure your institute will become the part of that quantum mission. Okay, so this is all from my end. If you have any query, so you may please ask. So I would like to say thank you to all of you. If you have any queries, so you may please ask.
Participants, unmute yourself. If you are having any doubts, please ask.
Good morning, madam.
Yes, ma'am.
Ma'am, you have explained some of the applications of quantum, and I would like to know about how can I apply this quantum technology in the field of biotechnology, ma'am.
Quantum technology to biotechnology.
Yes.
Ma'am, actually, as per my experience, I am not associated with the biomedical, but yes, the devices in which we are connected with the quantum materials and devices people to IIT Delhi. So definitely they are making the devices, because the first thing on which testing is going in is that we are able to make the qubits, right? But the testing is going on that either those qubits are able to communicate to each other or not. When they would be able to communicate to each other, then only our devices would be fulfilled. Okay, so it is a very initial stage. We are not at the part that we are thinking for that thing, because right now we are having the concern with the three applications, with the quantum communication, quantum sensing, quantum metrology, and quantum computing. So your quantum devices and materials are being designed. We are choosing for that only, that we are aligning with these applications or not. So for biomedical at present we are not able to see it, but yes, if we talk about the carbon nanotubes and single electron transistors, which are based on the nanoelectronics technology, so they are presentable, but at quantum level, it is not yet being proposed by anyone.
Okay, thank you, ma'am. That is, I wish to know, for example, if I am using any quantum technology and I am just making some measurement based on it in the biotechnological field, it would be of great help. So, in that concern, I have asked, ma'am. That is making a quantum measurement device. For that, which hub do I contact, ma'am?
Quantum material devices.
Measurement, quantum measurement.
Quantum measurements. Okay.
Yes.
At present, the testing is going on at IIT Bombay.
Oh, okay.
Yeah.
Thank you, ma'am. Thank you.
Or otherwise, you may approach to Indian INST Mohali also, Chandigarh.
Okay. Okay, ma'am. Thank you.
Ma'am, participants posted their questions in the chat box, ma'am.
Okay, okay. Uh, Thank you so much. Okay, thank you so much, Jana ma'am. Quantum computing in renewable energy, and if it helps to increase the efficiency. Okay. Actually, the same thing that was asked, that in a biomedical we are looking for this technology right now or not, and the same thing that for the quantum in renewable energy. As far as I already told you that at this moment, what we are doing at presently, that we are having the concept of quantum computing, right? But for quantum computing, we basically need the quantum devices, and for that quantum devices, we need the quantum materials. Okay, so for renewable energy, if our because at that state we are at that point that we have made the circuits devices, right? But we are at the state that whether they are able to communicate in between, they are able to entanglement or not. If they would not be able to entanglement, so that means we are at the very previous state we are. Okay, and yes, the things we already have, that is superconducting facilities we have, right? But at present, quantum computing for renewable energy applications, we are not watching it. We are watching it for the for only sensing purpose, that is for meteorology. Okay, for the communication purpose, we are looking for it. Okay, so this is a chain in which we are at a very initial state, because in the September 2024 we have started our work on quantum domain. Okay, so at that point of time, I'm not that much answerable to your questions, that when we would be able to do something for renewable energy through quantum computing. But yes, with the their current facilities are being provided by various institutes, various R&D labs, right? And those facilities are also giving high computational facilities to various institutes. Might be this answer will help you.
Any questions, participants?
Because after 5 to 6 years, we would be answerable to each and every questions. At present, we won't be able to. In the last week, I attended one FDP on the quantum devices and materials as well at IIT Delhi, and yes, we all are at the same phase. We are all at the very initial stage. They are one step ahead to us, but we are on the same phase, that we are new to this field. Because classical computing, after that, supercomputing facilities we have, right? And now we are talking about the quantum computing. So there are three computing things are going on in the market. Okay, any other question? Okay, if you have any other question, you may drop a mail also. Yeah, this is my email ID. Is it visible to all? Or, I will share the same detail over here also in the chat box. if your institute is the part of C2S program, right? If not yet, then please become and please follow the and become the part of India Semiconductor Mission. And the 2 persons from the VLSI background is required for this to access this facility from Ministry of India. I hope your institute is the part of that. If not yet, then please go ahead. Ma'am, please go ahead with your C2S program at your institute.
Yes, ma'am. Ma'am, in that CPS program, where they provide quantum facilities, quantum lab, ma'am?
No. This is purely for semiconductor mission, okay? And the major industrial tools access you will be able to get, all EDA tool access, right? And now that the facility I was talking about in my lecture, in my this session, that Param facility, right? Now C2S has adopted that Param facilities also, and that is supercomputing facility, and they are offering it right now. From the last 2 months, they have invented this facility, supercomputing facility, and they are giving it to those institutes who are already be the part of C2S program, and it's really commendable job they are doing it. So please take the advantage of all these initiatives which Government of India is making for us, for our students as well, for us as well.
Ma'am, for applying this quantum lab, what are all the things needed? I mean, facilities in our college, ma'am, to apply for this quantum lab. Yes, for this applying quantum lab.
Okay. Look, this is a very expensive things if you go on and on, okay? But yes, the first call has already been completed by the DST, Department of Science and Technology. August was the last week of August was the closing date of first call, right? So probably within a 6 month or 8 months, means within a year, second call will come, right? So who would become the part of that to want to establish, right, the quantum lab. They are having the condition that they would start a minor course in quantum, right? And that course has already been designed by AICTE. You have to incorporate that only, and there are 4 domains in which you could apply, right? First is quantum computing, second one is quantum material and devices, third one is quantum sensing, and fourth one is quantum communication. So from out of 4 domains, you could make a one proposal to establish your teaching lab at a UG level, okay? And there is a requirement of 1 PI, okay? And you require a 3 to 4 or maximum 5 team members could be there, and 1 lab technician would be there. And there is a requirement that the 3 team members, okay, would surely be available to do work in these labs, okay? And they are proposing they would get that lab for next 5 years, okay? They will give the whole grant in a 1 year for purchasing equipment and all that, and more that 75% grant would be come from DST, and 25% would be given by the institute.
Thank you, ma'am.
Further details you are able to get on a DST.
Vote of thanks. On behalf of the management, I take the privilege to propose the vote of thanks. I thank our beloved chairman and CEO, Sir Dr. Sai Prakash Leyamuthu, and our principal, Dr. K. Palani Kumar, and our HOD ma'am, Dr. G. Tamarai Chelvi ma'am, for their guidance and support. I extend my heartfelt gratitude to our resource persons who spend their precious time with us to share their knowledge and experience. Thank you very much, participants, for your interest and patience at each day. Your willingness makes us to conduct more development program like this. Thank you all. Thank you once again, ma'am. Thank you, participants.
Thank you so much. Thank you all. Thank you to the participants. Thank you to the organizing team. Thank you to the ma'am, and thank you to the institution. If you still have any queries, you have my email ID and phone number. You may drop a WhatsApp message also. You can drop an email also. And thank you so much, and thank you to the team. And have a nice day to all of you. Thank you once again.